Hello again. Once we cover the first part, which is the introduction to differential calculus, let's get started with this um, first topics. So our first topic will be relation, relations, and functions. And this is kind of recap of what we covered in the last period. Uh, Here, the first definition is the definition of a set. A set is defined in the intuitive way as a collection of objects. And most of the time, you will see in your textbook, um, in your other references, and some internet sites, that the objects and the set of objects are represented by capital letters. Let's say in this example, let's say A, and let's establish our set A with a list of these numbers. Let's say that our set A consists of the numbers 2, 3, 4, and 5. Uh, as you know, a set could be, in this case, a collection of numbers, but this can change. You can have a collection of any object, books, a set of notebooks, a set of toys, a set of light bulbs, a set of motors, or whatever you want. But in this particular case, we will handling numbers. So let's put some numbers on these subjects. Um, let's say, for example, that we have a set B, and for set B, we will have 4, 9, 16, and 25. Okay, so there are our two sets, set A and set B. And then what's the relation between set A and set B? Well, especially when we study infinitesimal calculus, which is differential and integral calculus, we will look all the time for the relation between variables, and the relation between the time and the hardness of the material, the relation between the time traveled and the distance traveled, the relation between uh, the amount of heat or the temperature versus the length of a certain object, and so forth and so on. So the relation is defined as some kind of rule that we need to define or find in order to satisfy the relation of or a pattern between any given values. For example, one of the simplest example to demonstrate this is an example of a relation or a rule is, let's say, the Cartesian product. The Cartesian product. Let's say, for example, that we want to calculate the Cartesian product for A and B. And what will be the results for the Cartesian product for A and B? Well, if we write that, we can uh, have the result here. So the Cartesian product is the ordered pair that we can form with these two set of objects. So will be the first one 2 comma 4, and then 2 comma 9, 2 comma 16, 2 comma 25, then 3 comma 4, 3 comma 9, 3 comma 16, 3 comma 25, then 4 comma 4, 4 comma 9, 4 comma 16, 4 comma 25, then 5 comma 4, 5 comma 9, 5 comma 16, and 5 comma 25. So this is the set that we form with the Cartesian product of A and B. And now we have a rule or a relation between the set A and the set B. And this rule or relation is expressed as the Cartesian product from uh, sets A and B. And what's the rule for that? What we need to know the ordered pairs that we can form with each one of these elements of A and elements of B. Okay, uh, let's now work with another uh, example of relation. What if we need to form or we want to find the set R? Okay, what's the rule for set R? Okay, let's say for example that we need to know or we want to find all values x comma y that belongs to the Cartesian product AB such that the product between x and y equals an odd number. Okay, um, why x and why we are using x and y? Well, because uh, we know that x is our independent variable, and we know as y is our dependent variable. So this is part of the common use notation. Okay, and we are using in this case the set A as our x variable and our set B as our y variable. So what we want here is to have a new set which we name R, and the rule for that is that we want to find all numbers x and y that belongs to the Cartesian product AB such that the product between them is an odd number. Okay, and what are there? They. Okay, if we take a look to our set, we will see that the product between these two equals 8. The product between these two equals 18. The product between these two is 32. This is 50. This equals 12. This equals 27. And this equals 48. This is equal to 75. This is equal to 16. This is equal to 36. This is equal to 64. And this equals 100. This is equal to 20. This is equal to 45. This is equal to 80. And this is equal to 125. So once we have the products of all the ordered pairs, we can now start looking for all those products that satisfies or makes this proposal or this statement true. So what about 3,9, which is this one? And what about 3,25, which is this one? What about 5,9, this one? And 5,25. So if we get the message, you will see that all these numbers here are odd numbers. And these odd numbers are the result of multiplying the A plus B from the set that we already come with after applying the Cartesian product. So now this is an example of relation between the elements of some sets. As you saw in other textbooks, one of the ways that we use to describe or define this subsets is the arrow diagrams. So let's write a couple of arrow diagrams here. Let me a couple of arrow diagrams, and let's say that this is our set A and this is our set B. And for set A we have 2, 3, 4, and 5. And for our set B we have 4, 9, 16, and 25. And you will see that these arrow diagrams are the same than our list. So this is one of the way that we can write a set, and the other way that we can write a set is using these arrow diagrams. So the relation in this case for R for this set A and B will be that we have a relation between the element 3 and the 9, between the element 3 and the 25, between the element 5 and 9, and between 5 and 25. So this is the description of the relation between the set A and set B using this R statement and making it true. Okay, uh, let's move on with another special type of relation. This special type of relation is named function. Okay, and there are some restrictions to the use of the word function, because even when a function is a type of relation, not all relations are functions. So functions belongs to the set of relations. And there are some specific rules to using the word function when we are using them for our calculations. And when a relation uh, does not accomplish the requirements to be a function, then there are another tools that we will use in the future to work with these relations that they are not functions. Okay, let's do an example. Let's say we have set f, which now is our function, and let's imagine that we have elements um, x comma y that belong to the Cartesian product AB, such that y equals x squared. Okay, so if we look our set A, B, the Cartesian product for A and B, we will come up with that we have here. The set F will be 3, 9, 4, 16, 2, 4, and 5, 25. Why that is true? Well, that's because uh, the square value of 3 is 9, the squared value for 4 is 16, the squared value for 2 is 4, and the squared value for 5 is 25. And all those numbers came from this Cartesian product from A and B. And this set is the set that makes this to be true. If we use our old guy here, our arrow diagram to represent this new set, we will let me write it in a, okay, there it is. Let's rewrite our set A, 2, 3, 4, and 5, and our set B, 4, 9, 16, and 25. This is our set A, this is our set B, and now we have this rule F that is establishing a relation between the set A and the set B. So if we want to describe this using our arrow diagram, we will see that there is a relation between 3 and 9, between 4 and 16, between the number 2 and 4, and 5 and 25. So this is the way that we describe the relation F, or the rule F, between the set A and the set B. And this is the new set that satisfies this rule right here, which is the rule of the function. So one of the requirements for a function is that we cannot have several values of y uh, from a single value of x. So in this case, there is a proof for that. Maybe you already know this. Let's say that this is a function x comma y, and this is the graph that represents that function. So if we have some value x of 1, and for x of 1 we have here a value y sub 1, and here another value y sub 2. So there is a test that we name the test of the vertical line. So if the vertical line, after plotting this relation, cuts the line in 2 points. So here we have 1 point of y and 1 point of y to the single point of SO1. So in this case, if the vertical line cuts the line of the function, this is not a function, and this is a relation. Okay. Um, in another example, let's say that we have x, another plot xy, and let's say we have the typical trig function sine of x. So here we can have, for example, let's say x of 1, x of 2, x of 3. And this is x of 1, x of 2, x of 3. If you see, this is the same value of y for 3 values of x. In this case, there is no problem because if we apply the vertical line, there is no way to cut the graph into places. So this is a function. So that only remember that we cannot have uh, more than 2 values of y, more than one value of y to a single value of x. In this case, if we are in doubt, we can perform the vertical line test just to identify a function from a relation. So these both are relations, but if this is happening to your relation, then we cannot name that as a function. Well, I hope this is all clear for you. If you have questions or you're in doubt regarding this material, please let me know. Um, Leave your comment or send a message or communicate via email so I can answer your questions. Bye.